Welcome to Krishna's classroom. We continue with our explorations of the concept of determinants. So, what have we done in the previous 4 lectures? We explored the problem of interpreting or giving a structural foundation for determinants in the case of n is equal to 2. And with the third and fourth part of these lectures, we went on to work with the case n equal to 3, which in a way assures us that we are on the right path. At the same time, developing the necessary notations to smoothly generalize for the case n. So, with this objective, we now begin with what are called n-linear forms on Rn. Let me make a remark that all the things I talk about can be worked with Rn replaced by Fn for any field F. Okay, but we will stick to Rn for the time. It can be Cn or any Fn for that matter. Right. So, the basic problem that you ask is that we know the definition of a determinant and it has amazingly beautiful properties, and suddenly you ask, if it has such amazingly beautiful properties, then it cannot be an accident. It should be truly coming out from some intrinsic structure. What is that structure? Now, this is what we have been exploring. So, it is not merely writing down the properties of a determinant that we are interested in, but essentially telling what determinants are intrinsically. And you know that it is all about defining a function from n by n matrices to a set of reals. If you are working with matrices over the real field with the real entries, but otherwise map from the n by n matrices with the entries from a field to F. Okay, right. Now, let us start exploring this. Now, we first introduce n-linear forms on Rn, what they are and how do they come into play. In fact, we have seen that it is the bilinear forms in the case of n equal to 2 and trilinear forms in the case of n equal to 3 that were significant in getting out the meaning of the determinants. Now, let us explore the notation and we will see how this notation was. So we take x to be equal to with appropriate structure. Now with a typical member of x is going to be x is equal to where xi belongs to R. Now we are interested in looking at, of course, it has the usual structure of adding component wise and scalar multiplying component wise and so on, and you can attribute some linear space structure for this, but that is not too relevant for us. Now what we do is, this is for I belonging to now let E1 En be the all right. So we define what's an n-linear form. We shall denote this by ln, so that we will write a function f. It's a real valued function on x with certain properties. Now what are the properties? Such that f is linear in each of arguments when other arguments are held fixed. Such a function is called a linear form. All right. What does this mean? That is, we have f of alpha I, beta I, say x I prime is equal to alpha I plus beta I prime xi. That means it is linear looking at this as a function of xi, that is the ith argument, leaving all others fixed. You see that it is linear with respect to that. Okay, with respect to the ith argument, where of course Rn and alpha I and beta I are. Now it is true for every I. Then you say this is f is an n-linear form on Rn. Okay. Now that's about the n-linear form. Let Ln, we'll use this notation, now we will just explore what structure you can attribute to Ln. Now, first of all, we observe that Ln can be made into a vector space. With addition and multiplication, as follows. Now we define for f plus g of and alpha f defined by alpha times f of where of course x1 x2 xn belonging to x and alpha belonging to. Now this is quite easy to prove, but what you have to prove is that f plus g is n linear. So also alpha f is n linear. Now that is simple to verify. So I leave it as an exercise to do that. Yeah. So we go to explore this vector space further. And if possible, try to construct a basis for that. Okay. So we will do the following. Before that, we make an observation. Now we prove the following or make this observation. Before that, we introduce certain notations. Let all functions on the set that is, if f belongs to Fn, implies, or let me use a different notation because I am using f there. So let me write, phi belongs to Fn implies phi is a map if phi is a function, is a map from 1 into Fn. Now this is not necessarily onto, in general onto, into. So phi is a function. That means phi I, okay, I is mapped to phi I. Okay, right. So we need this notation later. Now we also introduce notations, or you can write down phi in a new form. Phi we write as 1 n phi 1 so it's a map from the set of numbers 1 to n into itself. It's a function. Okay, so that's we denote by the class of such functions, we denote by Fn. You know that it's a finite class of functions. Now you see that this consists of precisely n to the power n elements. Okay. What I mean to say, there are n to the power n distinct elements in Fn. So we now introduce another handy notation. Define where E1, E2, etc., En form the standard basis for Rn. So that we have already said what exactly is E1, E2, En. So you see that this n tuple forms this n tuple forms a element in say the space X. Okay, so this belongs to X. So for every phi belonging to Fn, E phi belongs to X. Now we also define E phi tilde by E phi 1 tensor product E phi n. So we have defined two things. One is this one, that is this part, and then we have with the property that such that E phi equal to E phi 1 delta phi 1 psi 1 psi n. So this is the definition of this. Or this amounts to prescribing the following, that is, we fix So that amounts to the following. Okay, that amounts to the following. So we have, see, EI, so you have E phi 1 cross Now, the consequence of this is the following, that is E phi tilde over each side equal to 1 whenever phi equal to psi, and this is equal to 0 whenever phi is not equal to psi. So, in short, that E phi tilde is now defined, thus we assign real for E phi tilde at every belonging to So, for each fixed phi, we have this defined in this particular way, or this is a notation rather, whose action is defined on this. Therefore, at every okay. Now we leave it at that, and now we show that with this definition there exists a uniquely determined n-linear form associated with this definition, namely defines an n-linear form on X or n Rn. Okay. So that we shall show. So first let us observe that. We proved the following theorem before that. If f belongs to Ln, then f is completely determined by the numbers f of E phi phi belonging to Fi. This is the theorem that we prove. That means once you prescribe, once f is given, of course, as an n-linear form, then in particular it is defined at all these points. Now what we want to prove is that if you know the values of f at E phi, then a n-linear form on Rn is uniquely defined from this. That's what we want to prove. So let us prove this. Then you have, you know that each xi is a member of Rn, therefore then xi is uniquely represented as sigma j equal to 1 to n xij ej, because E1, E2, etc. En forms a basis for Rn. So each xi is a member of Rn, therefore this is represented by this, where xij's are unique scalars. Now we can work with this and then see what comes out. Okay. So let f belong to Ln. That means it's an n-linear form on Rn. So if so, what do we get? An n-linear form. Then we have f of equal to f of nj ej. Now let us use the n-linearity. Since f is n-linear, we have, if you expand this, so this is j equal to this is equal to f of summation over phi phi n f of E phi 1 E phi 2 E phi n, and which you can write as some sigma summation over phi C phi you will recall the notation of E phi, okay, where C phi is equal to into x2 phi 2 x n y n. It's a scalar. Okay. So you see that here, once you know f e phi 1, f at e phi 1, e phi 2, etc., e phi n, then f of x1, x2, etc., xn turns out to be a linear sum of that, where the scalars are obtained from the scalars from the representations for x1, x2, etc., xn. Okay, we vary over all phi, and there are n to the power n such phi's, so it's a sum involving n to the power n terms. Now this is what you get. Now hence the value of f is determined by the values f takes each cos phi belonging to phi. So you don't have to specifically say what exactly is this. All that we need is fix f at e phi 1, e phi 2, etc., e phi n, or rather capital E phi, then f is uniquely determined. Okay, so you don't need any more information about this. Now that is, this expansion is valid, that you can verify, and it's easy to verify this, and one can get this. For instance, you can check this in the case n equal to 2 and n equal to 3. Okay, so verify this before you prove it. So we'll just make some remarks. So in the case of n equal to 2, let us make some remarks before we go to, this is just to get a hang of this notation. In the case of n equal to 2, you are working on R2 cross R2. So the set of functions that we consider are E1, 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 E2, E2, E1, and E2, E2. So this is the set of E phi's that we consider. So this is essentially the collection of E phi. This corresponds to 4 functions. I mean, there are 4 functions defined like this. See, phi is a map from it's a function. So you have got, let me say, phi 1 to be phi 1 1, let me write, or let me write, yeah, phi 1 1 I write as of E1 equal to E1. This is phi 1 1. Phi 1, okay, phi 1 2 of E1 I write as E2 So that defines the function phi 1 2. Then you have phi 2 1 of E1, I define it as E2, phi 2 1 of E2, I define this as E1. And phi 2 2 of E1 I define as E2, phi 2 2 of E2 define as E2. So there are, you have 4 functions, phi 1 1, phi 1 2, phi 1 3, phi 2 1, phi defined in this way. Now this I can write as E phi 1 1, E phi 1 2, E phi 2 1 and E phi 2 2. So I write this as these are the 4 things. Now for the case we have, there are 27 functions of the kind EI, EJ, EK. Okay, so what you have is 1 2 3 going to, so let me write phi I j k of phi so we will define this, where ijk can be anything that belongs to 1 2 3. So ijk so there are so many phi ijk, so I can write this as E phi. So E phi, so you have E this collection you look at, where ijk belongs to 1 2 3. So you get 27 functions, and accordingly this you can write down the values of that. So I leave that as an exercise to you. Okay. So what you mean to say is that if f belongs to L2, then it is completely determined by the value of f at these 4 points. Okay. Similarly, if f n is equal to 3, if f belongs to L3, then it is completely determined by, f is completely determined if you know the values at E5 or E5 ijk, where ijk runs over 1, 2, 3. Okay. So that's the meaning of that. This is just a sort of explanation of what is happening. Now what we have observed is that the space of all n linear forms on Rn forms a vector space. So we have already seen that the space of let us designate this by x tilde. So let x tilde denote this vector space. That is the vector space of all Now you observe the following. I think we have already designated this. Okay, let's designate this by okay, right. Now what we observe is the following. Now we observe that each E5 tilde phi belongs to Fn. Defines a n-linear form on Rn with their prescription, the prescribed values at for psi belonging to okay. So what we have is this, that is, we have said that E tilde phi of E psi 1 whenever phi equal to psi equal to 0 whenever phi is different from psi. So at all E psi, fix phi. Once you fix phi, you have E tilde phi defined by the values it takes at E psi for all psi over the space of over the functions Fn. Okay. So they are already available. Therefore, every E phi tilde can be considered these n-linear forms also by E tilde phi. So we have the following, namely, we have now n to the power n n-linear forms defined on Rn. Thus we have now this is true for every phi belonging to what we are going to assert or prove is that the space Ln that we have designated is going to be going to have these E phi tilde as its basis. So theorem, we prove two things. forms a basis for and the dimension of Ln so this is one of the basic theorems that we prove. Okay. So let us have so given f, okay, so now we want to write this as a linear combination of this, okay. So you see that f is completely determined by the values this we know. So let us define f prime to be equal to summation over now you see this is A and this obviously belongs to Ln. Now we will prove that f prime at f prime at E psi equal to sigma phi belonging to Fn f E phi acting over E psi. Now let us evaluate this at E psi. Okay. So what about this? Suppose you evaluate this, use the property that E phi tilde E psi equal to 1 whenever phi is equal to psi, otherwise 0. So if you use that, we have f of turns out to be simply f of which implies E psi which implies f prime agrees with f at every E phi. Now one can easily show that now using this one can show that it's a routine exercise that phi of, or rather, what is that, f prime of the process is simple. Write x1 as a linear combination of e1, e2, etc., en, etc. All these exercise you write as linear combination of e1, e2, etc., en, and then use n linearity. Okay, so you can easily get that they are the same, right? Get the definition of see, we have f prime at each side equal to, what is it, f of each side. So use this. Okay, therefore we end up with the following representation, namely that f is equal to E phi tilde. Okay, so that is a, that means the collection of E phi tilde spans Ln. Now all that remains is to show that this is a basis. Now the next part is that suppose you know that the linear combination of E phi tilde forms an element of Fn. Suppose phi that is a linear combination of, this is the zero linear functional, the zero n linear form. Now this is the zero n linear form. You know that this is an n linear form, that's easy. Okay. Then what we have is zero is equal to Fn. This is true for every E psi. So in fact the evaluation of this over E psi is equal to 0, which in turn, now this is equal to what? This is equal to C psi. Therefore or in other words, that sigma C phi E phi tilde equal to 0 implies C phi equal to 0 for every phi belonging to. So that shows that is forms a therefore together with the earlier part of this we have E phi tilde is a basis for L. Okay. So the consequence is that the number of distinct elements in this collection is n to the power n. Therefore, the dimension of Ln is equal to n to the power n. The number of distinct elements this is easy to prove, simple combinatorial work. It is, that is, as many as the number of distinct functions so the dimension of hence the dimension of so that completes the proof of that. So in fact we have now got an idea of the structure of the space of all n-linear forms on Rn. Okay, that is the linear space structure of that. In fact, we exploit this, but what we want to do next is to explore what is called the alternating n-linear forms. Okay, so that is our next task. So next time we look at what are called alternating n-linear forms, and then through that we prove that the determinant comes out in a very natural way for any linear operator on Rn. That's our task. So I think the path is clear now, but we have to just go through the routine exercises. Once these notations are fixed, then everything is simple. In fact, it is amazingly simple notations evolved using this. Okay, thank you very much.